In the vast expanse of the late Jurassic, 150 million years ago, the land was a theater of giants. Forests of conifers and fern prairies stretched across a continent, a world ruled by a simple, brutal equation: eat or be eaten. In this world, the evolutionary arms race between hunter and hunted reached a fever pitch, producing some of the most spectacular creatures in Earth's history. But one predator stands apart, not just for its power, but for a profound and counterintuitive secret hidden within its anatomy. Now, let's open the fossil record and resurrect the story of this Jurassic titan. This is the world of Allosaurus fragilis, the different lizard. For millions of years, it was the undisputed apex predator of North America's famed Morrison Formation. Growing up to 10 meters long and weighing over 2 tons, Allosaurus was a superbly engineered carnivore. It moved on 2 powerful hind limbs, its body perfectly counterbalanced by a long, muscular tail. Its arms, unlike the famously reduced limbs of the later Tyrannosaurus, were formidable weapons in their own right. Each hand was equipped with 3 massive, eagle-like talons, hooked and sharp, designed for gripping and tearing through flesh. Its very presence would have cast a pall of fear over the floodplains. When we analyze its arsenal, the most obvious feature is the mouth, filled with dozens of serrated blade-like teeth. These were not the bone-crushing spikes of T-Rex. They were recurved daggers, constantly shed and replaced throughout the animal's life, ensuring they were always sharp. Fossil sites are littered with them, a testament to its ubiquitous presence and voracious appetite. For decades, our understanding was simple. Allosaurus was the quintessential big theropod, using its size, claws, and a powerful bite to overwhelm its prey. It was the lion of the Jurassic, a brute force killer. But the fossil record holds subtleties that challenge our assumptions. When paleontologists began to apply modern engineering principles to the Allosaurus skull, a startling paradox emerged. The skull itself is a marvel of construction, immense yet surprisingly light. It is more delicate than it appears, characterized by large openings called fenestrae, which reduced its weight without compromising its overall structural integrity. Using CT scans and finite element analysis, the same computer modeling used to test the stress tolerance of bridges and aircraft, we can reconstruct the forces this skull could withstand. The results are nothing short of astonishing. The calculated bite force of Allosaurus is remarkably weak for an animal of its stature. Its jaw muscles could generate a fraction of the power wielded by Tyrannosaurus rex, and even less than that of a modern-day saltwater crocodile. This discovery presents a profound biological puzzle. Here is the dominant carnivore of its ecosystem, an animal known to have hunted some of the largest and most well-defended herbivores of all time, from the armored stegosaurus to juvenile sauropods that would one day become titans. Yet the evidence from its own bones suggests it lacked the primary weapon we associate with apex predators, a devastating, bone-shattering bite. How could a creature with such a seemingly significant weakness dominate a world of giants? The answer is not in raw power, but in a lethal, specialized strategy that turned its entire skull into a weapon of shocking and unique efficiency.
The solution to the paradox of the Allosaurus's weak bite lies in reimagining the function of its skull entirely. We have been thinking of it as a pair of pliers designed to crush and hold, but the fossil evidence suggests a different, more terrifying analog, a battle axe. This theory, often called the hatchet bite hypothesis, repositions the Allosaurus not as a biter, but as a slasher, and it fundamentally changes our understanding of predation in the Jurassic. When we re-examine the skull through this lens, its strange architecture suddenly makes perfect sense. The large fenestrae and lightweight bones were not weaknesses. They were sophisticated adaptations for a unique method of attack. While the skull was not built to withstand the torsional, twisting forces of a prolonged struggle, biomechanical models show it was immensely strong along its vertical axis. It could absorb massive impact forces, provided they were delivered straight down. The true engine of this weapon was not the jaw, but the neck. When we analyze the vertebrae and the back of the skull, we find large, complex attachment points for an incredibly powerful and flexible neck musculature. Allosaurus could strike downwards with an astonishing force and precision. The hunting strategy that emerges from this evidence is one of calculated, brutal efficiency. The animal could open its jaws to an exceptionally wide gape, perhaps over 90 degrees. This action exposed the full battery of teeth in the upper jaw, the maxilla. Driven by its powerful neck, the Allosaurus would slam its head downwards onto the flank or back of a large herbivore, using its entire skull as a single serrated blade. The lower jaw, the mandible, did little more than stabilize the impact. It was not a bite in the conventional sense. It was a catastrophic chop. This method explains how Allosaurus could tackle prey many times its own size. It would not have engaged in a prolonged wrestling match with a 30-ton Diplodocus. That would have been suicidal. Instead, its strategy was likely one of ambush and attrition. A single, well-placed strike from this biological hatchet would have been devastating. The rows of flat, serrated teeth were not designed to crush bone, but to slice through hide and muscle, creating enormous, gaping wounds. We can envision the predator rushing from cover, delivering a powerful blow to a sauropod's leg or flank, and then immediately retreating to a safe distance. The fight was not won in the initial assault. It was won in the aftermath. Driven by instinct, the Allosaurus would then become a patient shadow. It would follow its wounded victim, perhaps for hours or even days, waiting for shock and blood loss to do their work. This was a far more energy-efficient and safer way to hunt the colossal herbivores that dominated its landscape. It minimized the risk of injury from a defensive tail whip of a sauropod or the deadly thagomizer of a stegosaurus. This slash-and-retreat tactic defines the ecological niche of Allosaurus. It was a specialist hunter of giants, occupying a role distinct from other predators. If we compare it to the later Tyrannosaurus rex, the difference is stark. T-Rex was a bone crusher, an animal built to end the fight quickly with overwhelming force, capable of pulverizing the skeletons of its prey. Allosaurus, by contrast, was a hemorrhaging specialist, a predator that relied on precision, specialized anatomy, and patience. This hypothesis also explains the surprising number of injuries we find in Allosaurus fossils. Skeletons show evidence of healed fractures in ribs, legs, and even jaws, injuries consistent with high-risk encounters. An ambush predator, even with a calculated strategy, is still engaging with dangerous prey. A mistimed strike or a desperate defensive move from its victim could have severe consequences. The fossils paint a picture of a life of violent struggle. The skull, therefore, represents a perfect evolutionary trade-off. It was made as light as possible to be wielded quickly by the neck muscles, yet remained just strong enough to withstand the enormous impact of its unique death-by-1,000-cuts hunting style. It was a high-stakes strategy, but for millions of years it was lethally effective, allowing the Allosaurus to reign supreme in a world of giants.
A scientific theory, however elegant, remains speculation without physical proof. The hatchet bite hypothesis provides a compelling narrative for how Allosaurus hunted, but to truly validate it, we must turn back to the stone and search for the killer's signature. Fortunately, the Morrison Formation is a rich crime scene, and the evidence is etched directly onto the bones of the victims. Paleontologists have discovered numerous sauropod and stegosaurus fossils bearing the distinct tooth marks of Allosaurus. When we analyze these traces, they tell a story perfectly consistent with the slash and retreat strategy. We find long, shallow gouges scraped across vertebral spines and ribs, marks left by the tips of the teeth as the skull was pulled back after a strike. We see evidence of feeding on carcasses, but crucially, the deep, bone-splintering puncture wounds characteristic of a crushing bite are conspicuously rare. The most dramatic evidence comes from fossils that capture a moment of violent interaction. At the Cleveland Lloyd Dinosaur Quarry, an Allosaurus vertebra was found with a perfectly circular puncture wound, a wound that precisely matches the terminal spike of a Stegosaurus thagomizer. This was a hunt that went wrong for the predator. Conversely, a Stegosaurus neck plate has been unearthed bearing a U-shaped bite mark that is a perfect match for the upper jaw of an Allosaurus. These fossils are unequivocal proof of predator-prey interaction, a snapshot of a life-or-death struggle. Perhaps no single fossil tells us more about the brutal reality of this existence than the specimen known as Big Al. This remarkably complete subadult Allosaurus is a case study in survival. Its skeleton is a catalogue of injuries, multiple healed rib fractures, trauma to its right foot that led to a crippling infection, and damage to its vertebrae. Big Al lived a hard life. These pathologies are not signs of weakness, they are a testament to the animal's resilience and the incredible risks inherent in its hunting strategy. To survive such grievous wounds, this creature must have possessed a robust physiology, but the sheer number of injuries reinforces the image of a predator that regularly engaged in violent, high-stakes confrontations. When we synthesize these different lines of evidence, the unique biomechanics of the skull, the powerful neck, the blade-like teeth, the trace evidence of tooth marks on prey, and the pathological record of injured skeletons, they converge on a single coherent conclusion. Allosaurus was not a simple brute. It was a highly specialized predator, an animal whose entire anatomy was fine-tuned for a specific and dangerous ecological niche, the hunting of megafauna. It overcame its surprisingly weak bite by evolving a different and arguably more sophisticated method of killing. Through the lens of science, the Allosaurus is resurrected not just as a monster of popular imagination, but as a complex and successful product of evolution. Its story, written in the language of bone and stone, reminds us that survival is not always about brute force, but about adaptation, strategy,
and finding a unique way to thrive in a world that is now profoundly and forever lost to time.